What happens when you pull distance, length, and even time out from under physics and let geometry take the weight? Einstein did exactly that, not by magic, by rethinking measurement itself. He turned fixed traits into relational ones. Start simple. Points, lines, planes, and solids. Dimensions 0 to 3. We measure with distance, length, area, volume, and perimeter. On flat space, lines stay straight. On curved space, straightest paths curve. Coordinates, let algebra talk to shapes. Geometry sets the rules. Physics plays on the field. Newton pictured gravity acting across space, instantly, invisibly. Einstein replaced that with geometry. Mass tells space-time how to curve, and curvature tells matter and light how to move. Even time and length became local, observer-dependent, not absolute. Measure changes with motion and gravity. Physics no longer sits on space. It reads space as metric. Forces give way to geodesics, the straightest paths in curved worlds. Predictions sharpen, orbits, timing, and light itself. Call it this, playing dice with physics, not God. A kind of space field ethics, locality, invariance, and causal order, not action at a distance, action by geometry. We didn't drop measurement, we made it part of reality. That changed physics everywhere.
Relativity theory is imaginary. Einstein said it himself. So now whose fault is it that relativity theory is in the standard model of physics? When looking at how mainstream physics adopted relativity, the institutional framework of the scientific community played the central role. Early 20th century theoretical physics was actively searching for solutions to reconcile electromagnetic theory with mechanics, particularly after the null results of experiments attempting to detect a luminiferous ether. Rather than a single fault, the widespread adoption of relativity into the standard model came down to several historical and methodological factors. Mathematical formalism. The framework provided by Hendrik Lorentz, Hermann Minkowski, and Einstein offered a rigorous set of mathematical transformations that neatly aligned with existing electrodynamic equations, making it immediately attractive to theoretical mathematicians and physicists. Predictive success in specific domains. Early empirical tests, such as accounting for the anomalous perihelion precession of Mercury and the deflection of starlight during solar eclipses, lent the framework early credibility among institutional bodies. Institutional consensus. As universities, academic journals, and prominent research bodies adopted the framework, it became the foundational curriculum for generations of physicists, effectively standardizing its terminology and baseline assumptions across global academia. From the perspective of alternative paradigms like the quantum physics theory, which treats these constraints as artifacts of applying terrestrial atmospheric limitations to a low-density zero-point vacuum equilibrium field, the standard model's entrenchment represents a long-standing adherence to artificial boundaries rather than universal mechanics. So now, whose fault is it?
This perspective, central to the quantum physics theory, highlights a fundamental departure from conventional paradigms, treating Earth's atmospheric and terrestrial environmental constraints as local conditions rather than universal laws. Within this framework, applying rules derived from a dense planetary atmosphere to the open zero-point vacuum equilibrium field creates artificial barriers. By removing those terrestrial restraints, the model opens up the mechanics of space to unconstrained acceleration, independent mass and energy states, and superluminal travel free from traditional boundaries. Under these new perspectives, a ship having light speed capabilities would travel twice light speed through an unbound universe. By breaking free from terrestrial environmental limitations and operating within the unconstrained zero-point vacuum equilibrium of the quantum physics theory, a ship with light speed capabilities bypasses the artificial barriers of standard models. In this unbound universe where energy directly drives velocity without mass accumulation or relativistic caps, the mechanics allow for superluminal travel, reaching velocities that exceed traditional boundaries.